Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. So in the last lecture we looked at essentially Jacobi iterative or iteration method, right, in which a solution of a linear system of equations can be found iteratively, right? So what we saw was essentially the unknown at any location xi can be found compared to the next iteration as a function of known values of xi, where I ranges from 1 to all the way to n, right? If we have a system of linear equations given by x equal to b. Okay, so in today's lecture, let us going to look at we're going to basically look at Gauss Seidel iteration method, or simply Gauss Seidel method, and then a variant of this is also known as the Gauss Seidel successive over relaxation method. So we're going to see both of these, and then depending on the time, we are also going to see how to essentially parallelize the Gauss Seidel method or the Gauss Seidel successive over relaxation. Okay, so this is also written as GS SOR. Fine. Okay, so one thing that kind of strikes to us is basically this particular update of the variable xik plus 1 kind of depends on the previous values of x at all the locations, or at all the locations that are already computed. So the specific formula we wrote basically was xik plus 1 equals 1 by aii, so that is the central coefficient, and then the right hand side was bi minus summation aij xj, where xj is evaluated at k, and then j goes from 1 to n, and of course j is not equal to I, right? That's what we have written, and this formula is valid for all I, that is I equals 1, 2, 3, n minus 1, and n, right? So that's what we have written. Now what we realize is that when we compute xi at any particular value, let's say at a particular value of I, that we already see that the xj at that xj values which are basically less than I. So let's say we are trying to compute xi, then we know that all the xj values where j is less than I are already computed, right? Are already computed at k plus 1th iteration, right? Only is that we are kind of not using them in the calculations in the Jacobi method. So this is what is kind of exploited in the Gauss Seidel method. So what it does is it will make use of the latest values available for x of I, depending on the value of I, whether I is whether the previous values of or x of j, depending on the value of j, it's going to use either the k values or k plus 1 values. Okay, whether j is less than I or j is greater than I. Okay, so that is the kind of philosophy in the Gauss Seidel method. Now if we talk about this matrix decomposition, they essentially representing in the matrix form, as we have seen in the last lecture, where a general iterative method is basically formed by splitting A into matrices such as M and N and so on. So we saw that in the Jacobi method, A was written as D minus L minus R, where D was the diagonal matrix, minus L was contains the lower triangular values, triangular elements of A, and then minus R contained all the upper triangular elements of A, right? A negative upper triangular elements of A. All right. So the Gauss Seidel method also uses pretty much the same decomposition of A. However, it's going to use it in a different way. Okay. So essentially, the way we send our the left hand side and the right hand side in terms of grouping them into m and n is where it kind of differs. So in the Gauss Seidel method, you're going to see, or you're going to write the iterative formula for any iteration of xi to the xi k plus 1 as d minus L, okay, times x k plus 1 equals, so it's basically x is your vector, equals r x to the k plus b. Okay, so unlike the Jacobi method where this was only d, in the Gauss Seidel method this is d minus L. That means the diagonal elements as well as the lower triangle elements are all considered as in the left hand side. That means that needs to be inverted. Okay, that means the iteration matrix, if we call it, so the iteration matrix for Gauss Seidel method comes out to be essentially inverse of this multiplied by r, right? So that means iteration matrix C for Gauss Seidel would be d minus L inverse multiplied by r. Okay, so that means xk plus 1 equals C Gauss Seidel times xk plus some d. Okay, so that would be the iterative formula. So xk plus 1 equals C Gauss Seidel times x to the k plus some d, right, where d is basically your d minus L inverse b. Okay, so that's the iterative formula. Now without again substituting all these values, what I would like to do is I would like to write the final component form, right, that we will use to calculate xi k plus 1 at essentially the k plus 1th iteration. Okay, so this, if you can prove that from this equation, that this xi k plus 1 for Gauss Seidel will come out to be equal to 1 by aii, that is the central coefficient, multiplied by bi as usual. And earlier we had only we had kind of summed all the elements into one term here, right, aij x j k. However, now that we are exploiting the values before j less than I are known, so what we have is we have two summations, one making use of xk values, the other making use of xk plus 1 values. Okay, so that formula, as you can see, comes from d minus L's inverse, right, because this matrix would be like what, d minus L inverse, or d minus L would be basically the diagonal elements as well as all the elements in the lower triangular matrix, right? So inverse of that, and then that basically will depend on all the values which are already updated. So that means b sub I minus aij xj of k plus 1, the updated values, and summation here goes from j equals 1 to I minus 1, right? And then you would of course skip j equal to I, so you don't have a term, and then you have aij xj values where xj is k, and then these values are for j equals I plus 1 to n, right? So just like what we have written before, only thing is that these terms are now made into two. One is for the the already known values and the already updated values, and these are the values from the previous iteration, right? So these are updated in the current iteration, already updated, and then these are previous iteration values. Right, still need to be updated. Okay, so that is basically the formula, where of course your I again goes from 1 to all the way to n minus 1 to n. Okay, now okay, so that is the formula for Gauss Seidel. Now what we realize is that this is of course Gauss Seidel will be faster in convergence. That means Gauss Seidel iterations will converge in less number of iterations compared to Jacobi, so it will be faster when compared to Jacobi. So that is very good when you have basically a serial or a sequential program. Okay, however, what you see now here is that the potential for parallelism is now restricted, because unless you calculate xj at this particular level of k plus 1, right, unless you calculate this guy, the calculation of the calculation of xik plus 1 cannot be accomplished. So essentially the potential for parallelism is now restricted because of Gauss Seidel. Okay, so the potential for parallelism is now restricted because of the dependency. So basically because of the Gauss Seidel iterations, right? However, the serial Gauss Seidel will be compared to the Jacobi, it will run faster. Okay, so we will see how to kind of avoid this problem, or how do we get about this, solving this issue of parallelizing Gauss Seidel. Okay, so before we do that, let us also explore a little bit about the Gauss Seidel successive over relaxation. That is basically an extension of Gauss Seidel. So this is successive over relaxation, also known as SOR method, GSSOR. So GSSOR is basically it is a modification of the Gauss Seidel in terms of adding a new parameter called relaxation parameter. Okay, omega, that kind of belongs to the real space. Okay, so some real number omega, and now that using that relaxation parameter, we can actually speed up the convergence of Gauss Seidel. Okay, so that means okay, so how this was discovered is basically very interesting. Essentially, before the advent of computers, we had humans or people calculating or doing calculations manually. So during that time, they realized that instead of adding a particular change delta x, or a particular change whatever you found, instead of adding this delta u, if you kind of multiplied this with a number which is basically greater than 1, then that kind of made the convergence faster. So that is how it kind of accidentally was discovered, and then as a result, that is the name is called over relaxation. So whatever you are trying to change, that delta, you are kind of multiplying it with little more than what it's supposed to be, and then that over relaxation made the method to converge faster towards the exact solution. Okay, now there is also another method known as under relaxation. Okay, as the name suggests, this will kind of restrict the change. Suppose if you found, let's say in solving for some u, you found that delta u should be the change at the next level, right, compared to uk, then instead of adding delta u, you would kind of multiply this with something number that is less than 1. Okay, so you would, let's say, multiply with 0.8 or something like that. That means you are restricting the change compared to what it is supposed to be between two iterations. Now this is of course this will kind of delay the convergence. So you will essentially end up doing more iterations. Then you might be wondering, why do we actually need this? This is actually needed in context of some non-linearities in the problem. Okay, so if there are some non-linearities, then you don't want the solution to blow up because of the large numbers that may be involved and the strength of the non-linearity. As a result, people will prefer under relaxation, in which will kind of help the system not blow up as such. So that means it will kind of it will delay the convergence. However, you will still get a converged result for strong non-linearities. When non-linearities are present, okay, so that essentially it will make it happen by constraining or restricting this amount of change, which we will not discuss anyway in the present lecture. But implementation of that is basically pretty much the same as this. Only thing is that if the value of omega is greater than 1, we call it successive over relaxation. If it is less than 1, we call it as under relaxation. Okay, fine. All right, so then how do we go about this thing? That means this particular parameter omega, what it does is it will basically modify the amount of essentially how much of the components, that is basically x1 to xi minus 1 at k plus 1 level, right, have to be contributed in comparison to the xi k values. So how much of these two have to be contributed will be dictated by this parameter omega. Okay. So that means what we do is that this new, so the value that is now computed using Gauss Seidel, instead of calling it as xik plus 1, we call it as some intermediate value, okay, which we denote using xi hat k plus 1. And then we have another formula which will relate xi hat k plus 1 to xi k plus 1, and this is where the amount of change is controlled using this parameter omega. Okay. So if I rewrite the expression that we had before, that is basically the expression for the Gauss Seidel, and I would denote the left hand side as xi hat. So to rewrite that, this is basically xi hat k plus 1 equals, right, we have 1 upon aii times bi minus j equals 1 to I minus 1 aij xj k plus 1 minus sigma j equals I plus 1 to n aij xj of k. Okay, that's what we have. Let's call this equation 1. Okay, that's your basically Gauss Seidel, but then instead of calling xi k plus 1, we call it xi hat k plus 1. Then we have now another formula which will basically tell how much of this xi hat k plus 1 should be used by adding it to the xik to calculate xik plus 1. So the other formula which is given by your successive relaxation is xik plus 1 should be, you essentially take xik and then you only add xi hat k plus 1 minus xik. So this is the delta change that is now dictated by Gauss Seidel. You multiply this using this omega. Okay, now omega can be some constant. Let's say this is some 1.2 or 1.1 or something like that. So that this is basically the change, and this change is relaxed in an over manner, right? It's kind of increased and added to the previous guess so that you obtain this current value. Okay, now what we do is I just have to now substitute for xi k plus 1 hat right here from this equation 1. So essentially substituting for xi hat k plus 1 into equation 2, I can write the final formula. Right, the final formula is xik plus 1 equals, we have xik has 1 here and minus omega here, so this is 1 minus omega times xik, and then I have plus omega times this value, that is omega times this entire expression. So I have omega times aii times bi minus aij xj k plus 1, j equals 1 to I minus 1 minus sigma aij xj k, where j goes from I plus 1 to n. Okay, so we have this one. So where I of course goes from 1 to all the way to n. Okay, so now this is the expression for your Gauss Seidel successive over relaxation method. Okay. Alright, now if you look at it in general, there is not much of a difference between Gauss Seidel and successive over relaxation methods. These two methods, they look very generic or very similar. They only differ by this parameter called omega, that is the relaxation parameter. That means whatever the limitations or possibilities that we discuss in the context of Gauss Seidel would also equally applicable for the Gauss Seidel successive over relaxation method. Okay, so that is what we need to keep in mind. As a result, now we will be free to just discuss Gauss Seidel method, and then you can always apply all the same principle to the successive over relaxation method as well. Okay. Now, as we saw before, the potential for parallelism is now restricted both in Gauss Seidel as well as in Gauss Seidel successive over relaxation because of this these kind of data dependencies, right, that are there in the equations. Okay, so these are well, in a serial sense, these were thought to be kind of useful because essentially you are using the latest value so that the convergence can be obtained in a less number of iterations. But from a parallel perspective, these are not really useful. Okay, or rather they hinder the parallel performance. Okay, now what we realize is that these xij, the dependency on xij k plus 1, right, is happening because of aij being non-zero, right. That means in the calculation of xik plus 1, the dependency on xjk plus 1, where j less than I, is happening because aij is not equal to 0, right? That means the matrix has a non-zero coefficient there. But so then we cannot really do much. However, you can think of a situation where aij's can be zeros, right? Let's say if aij are 0 for all these j less than I, that means then the dependency on xjk plus 1 will be gone, and then the equation will get restored to only dependence on xjk. So as a result, you can essentially achieve very good parallelism. But that is a kind of a hypothetical situation. But what we can see is that now let's say aij, not all aij are 0, rather many are 0. Okay, this is another scenario. Many are zeros, or rather we are talking about a sparse matrix, right? And that sparse matrix also happens to be a banded matrix, that we like what we saw before. If that is the case, then there will be only few aij's which will be not equal to 0, for which j less than I needs to be considered, right? That means this dependency would not turn out to be, will turn out to be only for few elements. Let's say you have n, which is, let's say, a large number, whereas this dependency for which aij is not equal to 0 will turn out to be maybe 3 or 5 or something like that. So that only that dependency can be somehow handled easily, and then the the potential for parallelism probably can be restored. Parallelism may be restored if you kind of work with a sparse banded matrix. Okay, and in fact that seems to be the case in most of the applications that we deal with. As a result, we can kind of generalize this for so what we're going to do next is we are not going to discuss about the dense matrices solution using Gauss Seidel in for parallel computation. Rather, we're going to only talk about banded matrices, right? Or solution of Gauss Seidel, or parallelization of Gauss Seidel, right? For banded matrices. Okay, because most of the simulations or physical properties or physical simulations you would do will essentially end up with banded matrices, and for which Gauss Seidel can be maybe potentially parallelized using some techniques. Okay, now in order to understand this, essentially how do we get the banded matrices and all, I'm going to now talk about a little bit about the the partial differential equations. And we are going to particularly look at one type of partial differential equation. That particular type is known as elliptic PDE, or elliptic partial differential equation. Okay, so I'm going to consider a two-dimensional domain. Okay, that means we're talking about xy coordinates, and then the corresponding indices we will use are ij. Okay, and then we are also we will kind of discretize and solve or set up an elliptic PDE. Okay, on this, so we try to solve this equation, some elliptic PDE on this two-dimensional domain. Okay, I will do this in order to end up with a essentially like a banded matrix. Okay, which is also sparse. I mean, of course, banded by we mean that already only the elements in the diagonals and the primary diagonal and the super and sub diagonals, or maybe few more diagonals, are non-zero. Everything else is 0. Okay. All right. So if we switch gears, we'll now come to the discussion of elliptic PDEs. Okay, elliptic PDEs are obtained in, let's say, in equilibrium problems. As well as in steady state problems, right? If you take steady state heat transfer or fluid flow, you can you end up with some elliptic PDEs, okay, and most likely in equilibrium problems in physics you will end up with PDEs which can be thought of as elliptic PDEs, okay. So from a mathematical point of view, okay, so there is a particular classification of PDEs into elliptic, hyperbolic and parabolic. We are not discussing that as part of the course, but if time permits, we'll look at how to parallelize the other two PDEs as well. But to get started, we will look at the elliptic PDEs, okay. Then from a mathematical point of view, what is an elliptic PDE? An elliptic PDE is one in which the solution at any point in the domain depends on all other points, right, or all other points in the domain. That means all the points are interrelated, okay. That means if there is a perturbation, so if there is a, that means you have a domain, okay, and then if there is, you know, and then there are several points on this domain, and then if there is a perturbation here, this is going to get translated, or this perturbation will be transported in all directions, and at theoretically at infinite speed, okay, in the instantly, essentially in the entire domain. So that kind of problems are governed by elliptic PDEs, okay. Now so in other words, the information propagates at infinite speed in the domain for an elliptic problem, and then elliptic problems are essentially very interrelated in terms of the grid points, and these are all kind of solved or formulated. So elliptic PDEs are formulated on closed domains with some specific boundary conditions on the boundary, okay. So that means if we have a kind of a domain at which we call it as, let's say, omega is the domain, and then let's say gamma is the boundary, okay. So we have to give, so this is a closed domain in which you can solve for an elliptic problem, and then gamma defines the boundary, and you have to specify the boundary conditions on this entire boundary, okay. Now what are the governing equations? So what type of equations fall into elliptic PDEs? Or examples of elliptic PDE, right? What equations can we call examples of elliptic PDEs? I think you probably already know very well what are the examples. Examples is the Laplace equation, right? Laplace equation is basically you have your nabla square for some phi equals 0, right, where this is your nabla, which stands for dou square by dou x square plus dou square by dou y square, right? All right, so your nabla, so essentially nabla stands for your I cap partial x plus j cap partial y, okay. That's your delta bar. And then similarly the other examples of elliptic PDE equations are the Poisson equation. The Poisson equation is similar to Laplace equation, but the right hand side will be a non-zero value. So this means del square phi equals some right hand side vector, right hand side value f, okay. Other examples are the famous Helmholtz equation, right. So this is basically your del square phi plus some coefficient alpha square phi equals 0, where of course in all these equations phi is your, or phi or phi is your unknown, right, to be determined. All right, So we are again considering, of course, as I discussed. Okay, now coming to the boundary condition. So what needs to be specified on the boundary? Now on the boundary, we can, everywhere on the boundary, probably the boundary conditions can also be of different types. The first type is known as the Dirichlet boundary conditions, in which you will specify the value of the unknown on the boundary. That means you will specify what is phi on the gamma equals some constant, right? And then other type of boundary conditions are known as the Neumann boundary conditions, right? In which you don't specify the value of phi on the boundary, rather you specify a particular gradient of phi. Let's say if the normal is n cap, then you specify the gradient of phi on the boundary to be equal to some value. Now this constant can be 0 as well, okay? And then of course you can also specify a combination of Dirichlet and Neumann on a particular, on the entire boundary or on part of a boundary, okay? It can be gamma 1, it can be gamma 2, which is basically, you know, some part of the boundary. So it can be, let's say, from here to here is gamma 1, here to here is, let's say, gamma 2, and so on, okay? And then you probably have something else here, let's say this is gamma 3, and so on, okay? Then you can have again a combination of Dirichlet and Neumann, that is known as the mixed boundary condition, or Robin's boundary condition. What we do is that you basically specify some constant a times phi plus b times partial phi partial equals some c, okay, where a, b, c are constants, okay? So you can even have a boundary condition like this, okay? So these are different boundary conditions. Of course, you can have again a mix of these on the entire boundary, or the entire boundary can have the same boundary condition as well, okay? Now let us consider, as we said before, we are considering a two-dimensional Cartesian mesh, okay? So in order to solve this particular PDE, we are going to discretize our mesh. That means we are going to create discrete points, or you know, a pattern like this, which we call it as a mesh, and we kind of convert our problem, which is a continuous problem as dictated by the governing equation, into a discrete problem. That means we are going to only obtain a solution only at these discrete points, okay? So we will convert our problem into a discrete problem, okay? So that means let me consider a two-dimensional Cartesian grid, okay? I will draw the two-dimensional Cartesian grid as like this. Okay, let's say it's all everything is uniform, although I am not drawing it like is nice and uniform. It is supposed to represent a uniform grid. Okay, let's say we have a grid like this. Okay, fine, all right. So that's what I have. Then this is basically, you have your x direction and y direction. Now I am using I for x direction and j for y direction, okay? So this is kind of not the same when we did matrices, because in matrices I represent the row. That means it went in the column wise direction, sorry, in the top down fashion, and where j was represented as in columns, then j went like this, right? So now it is different, okay? And then let us also call the distance between 2 points here as delta x, and the distance between 2 points here as delta y, and let us say both are equal to some delta, okay? And then now when we say we have discretized the problem, we are essentially saying we have these grid points where we would like to solve for the equation that we have written, right? So these are the grid points. I'm not drawing them, all of them, okay? Let me kind of draw these grid points here, okay? Then every grid point is kind of can be specifically located using the coordinates ij or indices ij. So ij or I comma j, fine. And then let us say there are m points in the x direction and n points in the y direction. And if the numbering starts from 0, 1, 2 all the way to m, we have the boundaries. Let's say these are all the boundary points on the entire domain, right? And then we have the interior points, okay? So these are all the ones in the interior are basically, these are the interior points, right? Or these are also called as near boundary, and these are interior points, okay? That means if we have m points in the x direction and n points in the y direction, we have essentially m minus 1 interior points in the x direction and n minus 1 interior points in the y direction. So the total number of points, interior points, are m minus 1 times n minus 1. And let us say we are using Dirichlet boundary condition, so we know the value of phi on all this entire boundary. Okay, that means the only unknowns are m minus 1 times n minus 1 values of phi are unknown, right, which needs to be determined, and the values on the boundaries of phi are already specified somehow. Okay, all right, then if we get started, what we have is we have del square phi equals f. Let's say if you work with the Poisson equation, okay, and then when you discretize, you know that you can write this in 2 dimensions as dou square phi by dou x square plus dou square phi by dou y square equals f. Now at any grid point ij, we can evaluate the value of f, that is basically f sub ij, and then this second derivative, as we have already seen, can be approximated using a second order accurate central difference formula, right, as because this is a derivative in the x direction and we are also at a particular j location, right. So if we are at a particular, let's say, j location and we are at a particular I location, right, so we can call this as I comma j or ij, and this point would turn out to be I plus 1j, and this will be I minus 1j, and one to the north is ij my plus 1, and the one to the south here is ij minus 1. Okay, in general you will start like this 0 1 2 and so on, right. So essentially if we use a double index notation, ij minus 1 and ij, so this will be 0 0, this will be 1 0 2 0 3 0 and so on, right. That's what we have, I index and j index, which will basically help us traverse all the elements in the 2-dimensional grid that we have shown. Okay, then if I use this, I can write this as basically phi I plus 1j minus 2 phi ij plus phi I minus 1j divided by delta x whole square. Similarly, in the y direction, we can write this as phi I j plus 1 minus 2 phi ij plus phi ij minus 1 divided by delta y whole square equals f evaluated at I comma j, right. So we have basically considered this stencil while evaluating dou square phi by dou x square, and we considered this stencil while evaluating dou square phi by dou y square, and then we have written the corresponding formula. Okay, that's basically I plus 1 I minus 1, j plus 1 j minus 1. Okay, all right, then let us see what we can do. We can now simplify this and rewrite this as by rearranging. So rearranging the formula, what we can write is, we can write this as phi I plus 1j, right, minus or plus 4, or I can say phi I plus 1j plus phi I minus 1j plus phi ij plus 1 plus phi ij minus 1 minus we have 4 phi ij equals delta square, right, this is basically the same, times fij on the right hand side. Okay, that's what we have, where I goes from 1 to all the way to m minus 1 and j goes from 1 to all the way to n minus 1. Okay, now of course we realize that if we are very close to the boundary, that means if you are on these points, let's say these points, this point, this point and these points, right, at these points which are near the boundary, they need a special treatment. Okay, so near boundary points need a special treatment. Right, now what is that? For example, let us say you have I equals 1, right, that means I am talking about this particular, all these points, and j goes from 2 to n minus 1. So if I say I equals 1, j goes from 2 to all the way to n minus 1. So for all the near boundary points, right, or near left boundary points, as an example, near boundary points, we can write this formula, right, as if I substitute for I equals 1 and j equals, I would just leave j as it is because j goes from 2 to n minus 1. So this will be phi 2j minus phi I minus 1 would be 0j plus phi 1j plus 1, right, plus phi 1j minus 1 minus 4 phi 1j, right, equals delta square f1j. Now what we see is that phi 0j is already known, so it need not be on the left hand side. This is already known, right? As a result, because this thing is already known, this should be sent to the right hand side vector. Okay, that means our equation becomes, at the near boundary points, phi 2j plus phi 1j plus 1 plus phi 1j minus 1 minus 4 phi 1j equals del square f 1j minus phi 0j, right? Phi 0j, that's what we have. Okay, so this is how you would modify at every boundary, at every near boundary. Fine. Now what we see is that, okay, well, we have a grid that is m minus 1 times n minus 1, that is great, but then we need to have a single vector, right? Now the vector itself, up till now we had one vector, let's say x or something, in x equal to b, and x had a values of 1 to n or whatever. But then now we have to somehow kind of organize this vector, because this particular phi, which is like our x before, has number of values is m by n, out of which m minus 1 times n minus 1 will be the unknowns, right? Everything else is known. So if we have a vector, and then if I arrange this vector in a row wise fashion, like starting with row and then going to the next row, so with preference for I would write this as phi 0 0 0 1 0 2, or I would say 1 0 2 0 0 1 0 2 0 all the way m0. Then I would come here and say this is basically phi 0 1 1 1 2 1 3 1 and so on. So if I go in this order, right, you go there, here, and then come here, then we basically have one vector that is kind of traversed, and then we would have a matrix as well. Okay, so essentially that vector would be phi 1 1 phi 2 1 all the way to phi m minus 1 1. Then we have phi the next one would be basically 1 2 phi 2 2 phi 3 2 and so on, right? And then finally you would have phi m minus 1 n minus 1. Okay, so that's your unknown vector. Now if you write them like this, then what happens is that now how does this equation that we have here, let's say this equation, get transformed, right? How does this equation get transformed? This equation will get transformed in a way. For example, if you are writing for ij, you have dependency on I minus 1 and I plus 1, and then you have dependency on j minus 1 and j plus 1, right? Okay, but then when you are writing phi as a row first order, phi I minus 1 and I plus 1 would come out to be the neighbors, and then j plus 1 and j minus 1 will come out to be neighbors, but then distant neighbors, right? These will be away by m minus 1 points, right? Because they only come after you finish. So these will be m minus 1 distant neighbors, right? So that means this particular coefficient will come there, and then these coefficients will come as neighbors, right? That's how we are arranging. That means if you remember these coefficients, these are all 1 1 1 1 and minus 4. Okay, so if I write them in a matrix form, we basically get minus 4 1, okay, all the way, and then after m minus 1 terms we get 1, and then we get 1 minus 4 1, and after n minus 1 you get 1, and so on. And then interior you will get 1 minus 4 1 and then 1 and so on, right? So essentially you get minus 4 comma 1. So that is how you will have a dependency. That means we end up with basically a you will of course get more ones here. Okay, so essentially these ones will follow here, right? So what we see is that we basically got a tridiagonal or a pentadiagonal system with diagonals as minus 4, and then we have super diagonals as 1, right, and then subdiagonals as 1, and then we also have more diagonals which are m minus 1 away from the main diagonal, right? So essentially this is how we have. Now there are two ways to look at this thing. One is of course on the right hand side you have this values. So if you are at the boundary, as we discussed, you get del square f11 minus, you will get those values, right? Phi 0 1 minus phi 1 0 and so on. And then if you are in the interior, you will only get some del square phi ij, right, and so on. At the boundary you will get more terms on the right hand side, right, similar to what we have here in this way. Okay, now this particular matrix, so this vector is of length what? This will be of length m minus 1 by times n minus 1, and this right hand side is also m minus 1 by n minus 1. Now this is where you need to pay attention. Now what will be the size of this matrix? This matrix is now m minus 1 by n minus 1 times m minus 1 by n minus 1. Okay, see, this is now is quite large, right? Up till now we were only discussing 1D, where if we had I equals 1 all the way to n, our matrix was n by n, right? Now we are discussing 2D, in which both our ij go from 1 to m and j goes from 1 to n, right? Then our matrix will be of the size m by n by m by n, of course, if you include the boundaries as well. Okay, if you exclude the boundaries, this will be the size. Okay, now that is what we need to keep in mind. So the size of this matrix now, which we have formulated, is m minus 1 times n minus 1 square. Okay, now of course in reality you will never formulate this matrix like this. You will always work with this formula itself. So you will not assemble the matrix. You will only be working with this particular equation. So as a result, you don't have to worry. Then you would only get m minus 1 times n minus 1 equations to solve, right? That's all you will get. You will never see the matrix. So your unknowns are m minus 1 times n minus 1, and those are the equations which you have to solve for. Now, how do you solve for this thing? Just like we have discussed, we can kind of solve for this. Now, I think I was about to say about this matrix, right? So this matrix can be thought of in a different way. One way is to look at is this is basically a pentadiagonal matrix, right? I mean, although we never formulate, it's kind of a good idea to see how or visualize how the matrix will be. That means because it has 5 diagonals and then everything else is 0, right? So whatever is not shown here, shown by dashes, is all zeros. Other way to look at it is basically like you have this, which is for m minus 1, and then you have the next layer for m minus 1, and then you have n minus 1 such repeats of m minus 1 such that this is m minus 1 by n minus 1, right? That means you basically have blocks of matrices here, right? Each block of matrix is a tridiagonal matrix. So basically you have a block tridiagonal matrix system, and each block is of size m minus 1 times m minus 1, and then you basically have identity matrices here on the top and bottom, right? So these are all identities for the block system. So this particular matrix that we the resulting matrix can be thought of as a pentadiagonal matrix with the other 2 diagonals are away, or it can be thought of as a block tridiagonal. It's a block, okay? That means you have blocks of tridiagonal matrices. You have one block here, another block, and so on, and each block is of size m minus 1 times m minus 1, and you have n minus 1 such blocks, and then you have identity matrices here, okay, on top and bottom. So it can be thought of as a block tridiagonal system or as a pentadiagonal system. I mean, this is only to know how, what the system is like, but we are not actually going to solve or apply in any methods compared to block tridiagonal system or so, okay? All right. Now you can of course draw a parallel to the 1D program we have kind of discussed before in the context of Jacobi. Let's say in 1D you have dou square phi by dou x square equals some f, right? Where the discretization kind of led to phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x square equals fi, right? That means we wrote this as phi I equals, right, phi I plus 1 plus phi I minus 1 minus delta x or delta square fi divided by 2, right? I think in the discussion of Jacobi, fi was set to 0, so you just had phi I plus 1 plus phi I minus 1 divided by 2, okay? All right. Now, if you recall your Jacobi method, so this is basically the 1D Poisson equation, right? What we have said. Okay, that means if you recollect the Jacobi method, what we did was now phi I can be updated as k plus 1 as use the values of k and then update phi I k plus 1. Okay. Now, of course, if you put in, instead of k here, if you put in k plus 1 for I minus 1, that basically gives you your which method? Gauss Seidel method, right? Because phi I minus 1 is already calculated when you are trying to calculate I. As a result, this is your Gauss Seidel method. Okay. Now, how do we write? Now, essentially, you update this for each of I equals 1, 2, all the way to n, right? And then you just keep doing it until you converge to some values, right? You guess with phi I k equals 0, you guess some values, and then update for k equals 1, all the values, and then keep doing that until you see there is no difference between phi I k and phi I k plus 1, where I goes from 1 to n. For all the values, if there is no difference, you say that okay, I have reached a converged state. Okay. All right. Now, how do I do this in 2D? It's very simple, right? You just have to take this formula and then send your phi j as your pose this as your update or unknown, right? Once you do that, okay. I think I should work with this equation rather than the boundary condition. Okay, I'll do that. That means I can write in a similar way as in 2-dimension Poisson equation. When you discretize, what you get is phi ij at k plus 1 equals phi I plus 1j plus phi I minus 1j plus phi I j plus 1 plus phi I j minus 1 minus delta square fij, right, divided by 4. Now, of course, the main point here is that what is known, what is unknown, that is already updated by the iteration, so that we can use the latest values in the context of Gauss Seidel. Okay, if it is Jacobi, everything here is all evaluated at level k, right? That is your Jacobi method. But then we are talking about now Gauss Seidel. In Gauss Seidel also, k plus 1 is I plus 1 is still not calculated, so this should be evaluated at level k, and j plus 1 is also not calculated yet, so this should be evaluated k, and then the remaining ones, that is basically I minus 1 can be evaluated at k plus 1, and j minus 1 can be evaluated at k plus 1. Okay, so that's what you do, and that basically gives you your Gauss Seidel method, or Gauss Seidel SOR if you kind of put in the omega parameter in there. Okay, so now this equation needs to be applied, calculated for each of the grid points, or for all the grid points of m minus 1 by n minus 1. Okay, all right. Okay, so that is the equation we need to solve for these many points iteratively. Okay, now as you can see, what we have done is we have reduced, because we have now resorted to a sparse or a kind of a solution of elliptic PDE, so we ended up with a matrix which is actually quite sparse. And then if you recollect our discussion at the beginning of the lecture, where if Aij, if many were 0, then life would have been easier to parallelize. And what we did is we did the same thing. So we, except for phi I plus 1 and phi ij plus 1, except other than so even if phi I minus 1 and j minus 1, only these coefficients are non-zero. Everything else, for example, I minus 2, I minus 3, all these are all 0, right? So we only have dependency on Aij, are only 2 non-zero Aij are there in any row, and then there are 2 non-zero Aij are there in any column for any given particular value. Okay, so as a result, what we discussed before is now obtained a sparse matrix in which many of Aij are 0, so that we can probably look at some potential parallelism when we try to solve Gauss Seidel or successive or relaxation for 2D elliptic problems. Okay, so that's kind of all the categories and constructs. Okay, so as of now, we are going to say there is still an issue that we cannot solve for this in a parallel way, because unless phi I minus 1j is computed, phi ij cannot be computed, and so on. So there is still an issue with parallelism. But in the next lecture, we're going to see how to avoid, essentially, or what are the methods with which we can kind of potentially parallelize Gauss Seidel or successive or relaxation methods, and we will also see if we can write a small piece of code and understand that. All right, I'm going to stop here for today. Talk to you in the next lecture. Okay, thank you.